In this video, we'll be covering section 1.2, basics of functions and their graphs. So just what do we know about functions and a little bit about their graphs. So first, let's define a relation. A relation is any set of ordered pairs. So it's just a relationship. The set of all first components is the domain. That's our input, or if we are graphing in xy, that's our x's. And the second set is called the range. So checkpoint 1, find the domain and range of the relation. Let's just do this one together. So the domain I'm going to write like this. So the domain set is all of the first values, 0, 1, 2, 3. That is the domain of this relation. And the range are all of the second values, or the y-coordinates, 187, 212, 225, and 238. That is the domain and range of this relation. Now, a function is a correspondence from a first set called the domain to a second set called the range. Now, it's different than a relation. It's a special type of relation that has this characteristic. Each element in the domain corresponds to exactly one element in the range. Okay, so let's look at example 2. Determine whether each relation is a function. So I've got 1, 2, 3, and 4. That's my domain. I'm going to write it like this, 1, 2, 3, and 4. And my range is 6, 8, and 9. So 1 goes to 6, 2 goes to 6, 3 goes to 8, and 4 goes to 9. Now goes to, in function discussions, we'll often say maps to. Now, is this a function? Does every element in the domain correspond to exactly one element in the range? So all we have to do is we have to look at the domain. For each value, does it only go to 1? And that's true here. 1 goes to 6, and 2 goes to 6, 3 goes to 8, 4 goes to 9. It is not a problem for two different values in the domain to go to the same range. So this is a function. We'll see a problem in the next one, and it looks like what we do is we switched the domain and range. So the domain of this is 6, 8, and 9, and the range is 1, 2, 3, 4. 9 maps to 4, 8 maps to 3, 6 maps to 1 and 2. This is a problem. If you have one element in the domain mapping to two different elements in the range, this is not a function. And in previous courses, you would have learned about the vertical line test. So this would fail the vertical line test. We'll talk about that again later. Functions as equations. Usually we give functions in terms of equations rather than sets of ordered pairs. And this represents all of the ordered pairs that make this equation true. So these are all the solutions. Okay. X is called the independent variable because it can be assigned any value from the domain. And y is called the dependent variable because its value depends on x. We plug in our value from the domain and then it maps to a specific value in the range. Not all equations with variables x and y are functions. So just because it has an x and y doesn't mean it's a function. If an equation is solved for y and more than one value of y can be obtained for a given x, then it is not a function. And we'll see that in an example. So example 3, let's determine whether these equations represent a function. So I'm going to solve for y. That's our step. So for this, we solve for y, and then we just analyze, we look at it and see if we could get one or more values for that. So I'm going to subtract this, y equals negative x squared plus 4. This only has one value possible for every x I put in, so this is a function. We'll see in part B examples that do not. So I would subtract x squared from both sides, gives me y squared equals, I'm going to write 4 minus x squared, and then we square root both sides. Now when we square root both sides of an equation in algebra, we have to include the plus or minus. So when I put in a value for x, let's say I put in 0, I'm going to get 2, but I'm also going to get negative 2. Okay, so y equals plus or minus. That means this is not a function. Now, if you are familiar with this graph, this is a circle, which doesn't pass the vertical line test. So a y squared is a key indication that this is not a function. All right, function notation. This is our f of x. This represents the value of the function at the number x. So one of the things we will do is we will evaluate functions using this function notation. Now we have a little diagram over here. A function machine represents the inputs and outputs. So this is our domain, any value we can put into the function. And then our output is f of x. So here on example 4, we're going to evaluate this function. F of x equals x squared plus 3x plus 5. So this means we're going to put 2 into this function wherever x is. So that's 2 squared plus 3 times 2 plus 5. So that's 4 plus 6 plus 5. So f of 2, or this function evaluated at 2, equals 15. Now we get more complicated. We have f of x plus 3, so I'm going to put in x plus 3 wherever x is. So f of x plus 3, that means we're not going to come down to a single number, but we'll have a new function. So I've got x plus 3 squared times 3 plus 3 times x plus 3 plus 5. So I need to FOIL this. X squared plus 6x plus 9 plus 3x plus 9 plus 5. And I'm going to simplify that by combining like terms. I get x squared plus 9x plus 23. Now we can also just plug in negative x. This is going to be useful for us later on. So I've got negative x squared plus 3 times negative x plus 5. So this becomes negative x squared is just a positive x squared minus 3x plus 5. So note that this didn't change a whole lot, but it did change this plus to a minus, and that will be valuable for us later when we talk about even and odd functions. So I mentioned the vertical line test a couple times. If any vertical line intersects the graph in more than one point, the graph does not define y as a function of x. And that's because for one domain there are multiple possible outputs in the range. So that would fail the vertical line test. This is not a function. And if we, see if I can do this, if we take this vertical line test, if we take a vertical line and move it along, we've got to check the entire length. Now this straight line will be a function. This parabola, notice it does not intersect, the vertical line does not intersect more than once. As I move this back and forth, and as we move it on D, that does intersect. So we have a function, and not a function. Now, graphs are a way to visually represent information, whether that's a bar chart or a scatter plot. But functions, it's no different. So we need to make sure we understand all the information that's being conveyed. And that's the bulk of what this unit is about, this portion of the unit. So we could have closed dots, open dots, or arrows. So this is just a review. A closed dot indicates that the graph does not extend beyond this point, and the point belongs to the graph. So if we have a function like this and a closed dot, that means this is part of the graph, but the graph does not extend beyond that point. If we have an open circle or an open dot, it does not extend beyond this point, and the point does not belong to the graph. And then if we have an arrow, it means it continues indefinitely in the direction in which the arrow points. So let's analyze the graph of a function. Example 7. The human immunodeficiency virus, or HIV, infects and kills helper T cells. Because T cells stimulate the immune system to produce antibodies, their destruction disables the body's defense against other pathogens. By counting the number of T cells that remain active in the body, the progression of HIV can be monitored. The fewer helper T cells, the more advanced the disease. Without the drugs that are now used to inhibit the progression of the virus. Figure 1.21 shows a graph that is used to monitor the average progression of the disease. The number of T cells f of x is a function of time after infection x. So explain why f represents the graph of the function, of the graph of a function. So this is just a vertical line test. If we drew a vertical line and went through this, then that shows that we don't have multiple outputs for a single input, or multiple values in the range mapped from one value in the domain. So use the graph to find and interpret f of 8. So what f of 8 means, we're going to come over here to 8. We go up to where the function is, and we think of this point here on the graph. So that means f of 8 equals 200. And what that means is 8 years after infection, there will be, on average, 200 T cells per milliliter of blood. Okay, let's add that, per milliliter of blood, just to give those units. For what value of x is f of x 350? Okay, so what we're going to do is we're going to come here. So last time we found the x value, the years, and went up to find f of x. This time we're told f of x is 350. So here's 300. There's about 350. I would say that's right at about 6 years. So let's see, this was b, c, x equals 6. Describe the general trend shown by the graph. Generally, we can say as time increases, T cell count decreases. If we wanted to be more specific, we could say drastic decrease of T cells in the first 6 months, and then an increase of T cells in the second 6 months. Then a gradual decline over the next 10 years, as far as our data has been given. All right, let's look at identifying domain and range from a function's graph. So again, the domain is the set of inputs found on the x-axis. Okay, so this diagram really helps us visualize that. Here's the domain. Now we use the brackets because we have closed dots. If they were open circles, we'd use parentheses. So this represents the domain. And then the range is found on the y-axis, so we bring that from the highest point to the lowest point, and that is the set of outputs found on the y-axis. So we can either use set builder notation or interval notation. So these two represent the domain of this graph to the left, this semicircle. Set builder notation says the set of all x such that x is greater than or equal to -4 and less than or equal to -2. So these bubbles here, text bubbles, gives us how you say that. And then -4 to 2 is interval notation. Usually I tend to interval notation. There are some functions where set builder notation is more appropriate and easier to use. And then the range, same thing. We're going to be looking here. Notice on the y-axis that's from 1 to 4. So set builder notation, all y such that y is greater than or equal to 1 and less than or equal to 4, or the interval notation just from 1 to 4 using the brackets. So example 8, identify the domain and range of function from its graph. So let's see how I write this. Domain, I'm going to write the domain. We use brackets from -2 to 1, and the range is 0 to 3. Again, I'm looking on the x-axis here from -2 to 1. Any point where you have the function go to the x-axis, that needs to be part of the domain. And similarly, any point on the function where you can go left or right to the y-axis, that needs to be part of the range. So on B, the domain will be parentheses -3, because we have our open circle, to 2, close with a bracket. And the range, it looks like we go from 1 to 2. On C, the domain goes from -2 to 1. Domain from -2 to 1 with a parenthesis there. And the range, let's see, this is our lowest point, that's our highest point. So that gives us 1 to 5. Now notice this is bracket on both because it equals, the function is evaluated there or has a value of 1. Let's see, D, let's see, this has an arrow, it's continuing on forever, so the domain is parentheses, -infinity. We always use parentheses with infinity to 4 with a bracket. And the range looks like 0 to +infinity. That's going to keep going up, not that drastically, but it'll keep increasing to infinity. E, this is for the domain when I'm going to use the set builder notation. X such that x is, let's see, less than or equal to, greater than or equal to 1 and less than, not equal to, less than 4. Because the range, I'm just going to say it's y such that y is or y is equal to 1, 2, 3. Because it's only these distinct values, it's not a continuous function going up. So that's example 8. Identify intercepts from a function's graph. A function can have more than one x-intercept, but at most one y-intercept, because if it had more than one y-intercept, then it would not be a function. So here are the x-intercepts. Sometimes we just list them out. Other times you might be required to list the coordinates like that. Those would be the x-intercepts. And that finishes our section. Thank you for watching.